In today's lecture, we start a new chapter on the discrete time Fourier transform, or DTFT. In this lecture, I want to define what do I mean by DTFT and its inverse, and we'll talk about some examples on computing the DTFT, and then we'll talk a little bit about the convergence of the DTFT. Let's start by defining the DTFT. So the DTFT, which is the discrete time Fourier transform, as the name suggests, is applied to discrete time signals. And for any signal x of n, the DTFT is defined as follows. So the DTFT of x of n is capital X of ej omega, and it's the sum over n of x of n e minus j omega n. Now you can see here that the DTFT is a function of omega. If you want to be maybe more rigorous, it should be written as x of omega because it's a function of omega. But the convention is that we write it as x of ej omega to say that it is the DTFT. So whenever you see x of ej omega or y of ej omega or h or capital H of ej omega, this means that it's the DTFT of the discrete time signal. Now, if you think of it a little bit, you can see that there is a strong connection between the DTFT and the Z transform. Actually, the DTFT is the Z transform evaluated at the unit circle. So if this is the unit circle here, so any point on the unit circle, any point Z here, is equal to ej omega, right? And then if you take the Z transform of the signal, so x of Z is equal to sum over n of x of n z to the power minus n. Now, if you take Z equal to ej omega, so x of ej omega is going to be equal to sum over n of x of n ej omega to the power n, which is the sum of over n of x of n ej minus e minus j omega n. And this is exactly the connection between the Z transform and the DTFT. So here we say that the Z transform of a signal is the DTFT of a signal is the Z transform x of Z evaluated at Z equal to ej omega. Now, given the DTFT of a signal, which is x of ej omega, we can recover the discrete time signal x of n using the following inverse DTFT formula. So x of n, the value of the signal at time n, is 1 over 2 pi, the integral between negative pi and plus pi of x of ej omega n d omega. And we're going to use this formula many times in the examples. An important property of the Z transform is that it is periodic in omega and has period 2 pi. So to give you an example, so let's suppose x of ej omega is a real signal, or if you take the amplitude of it, so let's suppose that x of ej omega looks something like this. Let's suppose that it is complex, so let's take the amplitude out of it. So on the axis here you have omega, and let's suppose this is the interval between negative pi and plus pi, and let's suppose it looks something like this. Then it has to be repeated, so because it has period equal to 2 pi, so here if you have here would be minus pi and plus pi, so this would be 2 pi here, and 3 pi. So what you would have something like this here, and again and again, and here the same thing. So here we would have negative 2 pi, negative 3 pi. So this is one period here, this is another period here, and here another period. So you would have, so it must look something like this also. Now, why this is happening? So if you want to see it intuitively, the Z transform interpretation of the DTFT is helpful here, because we know that the DTFT is the Z transform evaluated at the unit circle. So if you're evaluating the function x of z here to get the Z transform, so let's suppose this is Z equal to EJ omega, and this is the angle omega, or let me use the in green, or you're evaluating at this point here, which is at omega plus 2 pi. So let's call this Z prime equal EJ omega plus 2 pi. These are actually the same 2 points, so it doesn't make a difference. And for this reason, we have the following property, which is basically summarizing the periodicity of the DTFT. So we have the property that x at EJ omega is equal to x at EJ omega plus any multiple of 2 pi plus 2k pi if you want. And here I prove the property, the periodicity of the DTFT in a more rigorous way, but if you understood it from the unit circle interpretation, it's exactly what's going on. So if you just plug in the formula, x of EJ omega plus 2 pi is equal to the sum over n of x of n, e minus j omega plus 2 pi times n. It's the summation over n again of x of n, and here I can separate the exponentials. So it's e minus j omega n, e minus j 2 pi n. Now if you look at this guy here, this point here is e negative j 2 pi n, so it's the complex number with the root unity, and the angle is negative 2 pi n. So you're making multiple of 2 pi's n times. So you're going to end up being here. So this is equal to 1, and then you're done. So that's what this is staying here. So this shows that the DTFT is periodic and has period equal to 2 pi. Let's start with an example. So the example is the following. Find the DTFT of x of n equal to a to the power n u of n, where u of n is the step function. And here we have that the magnitude of a is less than 1. So you probably recognize this example from the Z transform formula, but let's do it here. So x of n is equal to the sum. So here we have to start at 0 because u of n is 0 for n negative. So to plus infinity a of n, or if you're confused, so this is this. So this is the sum from minus infinity to plus infinity a of n, u of n, e minus j omega n. But u of n is 0 if n is strictly negative. So now my summation starts at 0. So I'm gonna get a of n, e minus j omega n. And this is sum from n equal to 0 to infinity of a e minus j omega to the power n. And now you can see that this is a geometric series. And then so this is equal to the first term of this geometric series corresponds to n equal to 0, which is 1 divided by 1 minus a e minus j omega. And this is true because true if and only if a e minus j omega is less than 1, which is the magnitude of a is less than 1, which is satisfied here. So this is basically the DTFT of the exponential series. And if you remember from, if you want to go back to the Z transform, we know that x of z is equal to 1 over 1 minus a z minus 1, and this is just So this means that x of ej omega, you just plug z equal to ej omega. So it's 1 divided by a, 1 minus a e minus j omega. So you get immediately the result. And this is exactly what I did here in this slide, maybe in a cleaner way, so you can have the different steps. Now let's double check that the inverse formula of the DTFT works. So let's suppose the problem was this. Given a signal with the following DTFT, so x of ej omega is equal to 1 divided by 1 minus a e minus j omega. Find x of n, or x of k here I call it. Doesn't matter. So let's suppose that we're doing the inverse problem. So we're given the DTFT and we want to find the signal. So how can we do this? And we know to find the inverse DTFT, we have to find the signal from its DTFT, we have to use the formula of the inverse DTFT. So we know that the value of x at k is 1 over 2 pi, the integral between minus pi and plus pi, 1 over 1 minus a e minus j omega, which is this, which is the DTFT, times e j omega k. So now, maybe one thing that I want to emphasize here is that this k here gives you the value of the signal at time k. So if you want it at time n, you multiply by n. If you want it at 10, you multiply by 10. So that's the relationship between the value of the signal and the DTFT. So let's do this integral and see what we get. So here I have the different steps, so let's do it. So I have x of k is, I'm just applying the inverse DTFT formula like I said. So this is actually, this part here is x, this part here is x e j omega. So I'm just applying the formula. Now if you look at this integral here, it's a little bit difficult to solve. So you have 1 over e minus a, e minus j omega, e j omega, and maybe so maybe one way to solve it would be to write down this sum here, or this fraction here, as the geometric sum. So what you would do is, then what you would have is, this would be the sum from n equal to 0 to infinity of a and e minus j omega n. And then here you have e j omega k, so you would get e minus j omega times n minus k. So if you got confused, what I did here is just replace this part here by sum of n equal to 0 to infinity of a n e j omega n, and of course here the assumption is a is less than 1, the magnitude of a is less than 1. And now now I get this step here, and then I can bring the integral to the inside, and then I can take a is a constant and 1 over 2 pi is a constant, so it's going to be the integral of minus pi plus pi e minus j omega n minus k. So let us try to find this integral, and let's call this n minus k to be equal to m, which is an integer. So I'm going to do it here on the left. So the question is, what is the integral from negative pi to plus pi e minus j omega m d omega? So we know that this is equal, this is an integral of an exponential, so this is going to be equal to minus 1 over jm e minus j omega m evaluated at negative pi and plus pi. Notice that because you're dividing by m here, so this is only valid if m is different than 0. We'll get back to the case where m equal to 0 later. Now what we get here is minus 1 over jm e minus j omega pi minus e j, here we're evaluating omega, so let me erase this. So this would be E minus J M pi, and here minus EJ M pi. Right, so, and now, so we know that here, so here you're doing, so this guy here is either, so let's look at EJ M pi. So you're doing M rotation in each one of an angle of pi. So this would be either a +1 or a -1. So if it's pi, so this would be this number here, if M is equal to 1. So this would be -pi here, E minus J M pi. And E J M pi would be, you're doing this guy here. So it's the same, it's basically the same point here. So these two things, E negative J M pi and E J M pi, are the same point, and this is equal, so the integral is equal to 0. Or you, or this, you can write this as a if you want another way to see this, this is, if you use Euler's formula, so this is equal to -2j divided by jm sine of m pi. And then you know, sorry, this is m. And you know that sine of m pi is always equal to 0. Now, so this integral is equal to 0 whenever n is different than k. So this is why I say here. So if n equal to k, meaning m is 0. Otherwise, so this is equal to 0 if m is different than 0. So well, here let me maybe whenever n is different than k. Now for n equal to k, the integral would be, is just easy, that the integral is actually the integral from minus pi to plus pi of 1 d omega. So this would be omega minus pi plus pi, and this would be equal to 2 pi, right? And this is what I have here. So you're gonna get, so all the terms in the summation here, all the terms here are going to be equal to 0 except when n is equal to k. And in this case, I would have this term would be a to the power k, 1 over 2 pi, the integral from minus pi to plus pi, minus j omega k minus k d omega, and this integral here is equal to 2 pi, because we just showed that this is true. So this is, sorry, this is 2 pi. So you get the result, which is a k. So which is x of k. So you recovered the signal from its DTFT. Another example is to find the DTFT of the impulse functions. So x of n is delta of n. So it's just an impulse at n equal to 0 here. And then if we just apply the formula, we know that x of e j omega is equal to the sum over n of x of n e minus j omega n. So this will give me, and we know that x of n is 0 except when n equal to 0, because it's the impulse. So this would be x of 0 e minus j omega of 0. So this would be equal to, x of 0 is 1 because it's the impulse. And this tells you that x of ej omega is just the constant 1. So you can see already it's also, I mean, trivially periodic because it's the same everywhere. So you can see the calculations here, and the result to keep in mind is that the DTFT transform of the impulse function at n delta n is x of ej omega is equal to 1. So it has frequencies on everywhere, the same amplitude of frequencies, which is 1. And usually when we want to plot the graph of the DTFT, since it's periodic, it's enough to plot it in a period equal to 2 pi, and we typically choose the interval from minus pi to plus pi. Now let's consider a third example, which is to consider a low-pass filter here. And if you look at the graph here of the low-pass filter, you can see it's a low-pass filter with cutoff rate lambda, because it's cutting off, it's 0 for frequencies or omega, or the corresponding frequencies that are greater than lambda, right? So this is a low-pass filter, and like I said, we usually just plot for the DTFT the DTFT in the interval negative pi plus pi, but what we mean here is that it's actually being repeated, so you have all these repeated at infinity every 2 pi. Okay, so the question is, given this low-pass filter, again, it's a low-pass filter with amplitude 1, because it's only keeping the frequencies between 0 and lambda, right? And it's zeroing out everything outside this interval. And the question is, find its impulse response. Now, to find the impulse response, we just have to apply the formula of the inverse DTFT. So h of n, the value of the signal or the impulse response at n, is 1 over 2 pi. The integral from minus pi to plus pi, x of ej omega and d of omega. So here there is a typo. It should be capital X, and I'll fix it later. And this would be equal to 1 over 2 pi. Since x of ej omega is 1 between negative lambda and plus lambda, so we get the boundaries here, and it's 0 outside, so we get this integral here, and this is an easy integral because it's an exponential, so it's 1 over 2 pi 1 over jn ej omega n evaluated between lambda and minus lambda. So in the end you get 1 over 2 pi 1 over jn ej lambda n minus 1 over jn e minus j lambda n, and then you can use Euler's formula to get that this is 1 over pi n sine of lambda n. And this is the impulse response of a low-pass filter. Now if we plot this, so if you look, so obviously, so this looks like the sinc function if you've seen it before. And if you plot, for example, the function, if you think of x as real, so if you plot the continuous function, it would be f of x equal to 1 over pi x sine of lambda x. So if you plot this, you're gonna get the plot on the next slide. So it looks something like this. So you can see it's like a sine, but it's being damped as with time. And the most important thing is that the corresponding filter is non-causal, because it has non-zero component in the negative time. So it's non-causal system, and this is why when we try to build a low-pass filter, we cannot build a perfect low-pass filter, but we have to have an approximation of it. Now actually the signal is sampled, so it actually looks something like what I have on the next slide. So the signal looks something like this here. So it's a sampled version of what you have below. And again, it looks similar to the sinc function. So similar to the Z-transform, where we had to talk about the regions of convergence. Here we don't have a region of convergence, but we must ask, or we must be always careful whether the sum converges or not. And for instance, if you revisit one example that we had, which was this signal x of n equal to a n u of n, the DTFT converges or exists if and only if the magnitude of A is less than 1. So in general, because the DTFT involves an infinite sum, so it could be the case that it does not converge and does not exist. Now, we have sufficient conditions for existence, but they're not necessary. So the two sufficient conditions for to guarantee convergence are either the sum has to be absolutely, the signal has to be absolutely summable, meaning the sum of the absolute value of x of n is finite, or square summability, meaning the signal has finite energy, meaning the sum over all n of the magnitude square of n of x of n is bounded. So if one of these conditions, only one, if one of them is satisfied, this means that the signal, the DTFT of the signal exists. But the DTFT of the signal may exist without these conditions being satisfied. So they're not necessary conditions. They're just sufficient. Now, the DTFT, like I said, you have to be a little bit careful and worry about convergence. But for the inverse transform, you don't have to worry about this because it's just an integral, and as long as and it's an integral over a finite length, so typically there should be any problem given that x of ej omega is somehow well behaved. So that is to say, you don't need to worry about the convergence of the inverse of the DTFT. No, now let's end up with some small questions that you can solve at home and to test your knowledge so far. So the first question is to find the DTFT of the following signal is 1 over 2 to the power absolute value of n. So the signal would look something like this. So the signal is symmetric over around the y-axis, because it doesn't matter whether n equal to plus k or minus k, it's going to be the same. So it looks something like this. So it's going to look, I mean, at least in it's the discrete version of this. So find the DTFT of the signal, and then if you want to, an additional problem is that given that DTFT, try to recover the signal by applying the inverse DTFT formula. And the second two questions are about convergence. One is about the step function. Prove that the step function is neither absolutely summable nor square summable. So it doesn't satisfy any of these two conditions that we talked about, but this doesn't mean anything if it doesn't satisfy these two conditions, because it can still be, it can still have a DTFT. And the question here, does it have a DTFT? And I think we're going to answer this question later in future lectures. And now the third question is a third example about a signal which is x of n equal to 1 plus 1 divided by 1 plus the magnitude of n, or the absolute value of n, and find or show that it's square summable, but it's not absolutely summable. And this brings me to the end of this lecture.